Hi everyone, thanks for having me. My name is Antoine Caillon. I'm currently a PhD student at IRCAM in Paris. And today I'm going to talk about our work on streamable neural audio synthesis with non-causal convolutions, which can be roughly translated as making deep convolutional networks work inside real-time frameworks. So there have been a lot of work recently on trying to apply deep learning models to address very specific audio tasks, such as classification, with, for example, pitch prediction or transcription, transformation tasks, such as restoration of historical recordings or source separation, and lastly, generative tasks with the recent Jukebox and Musica, which have provided very convincing unconditional generations. And those work are really improved the state of the art for each of their individual problems. And one of the reasons why those work are so successful is because they use, for the architecture, the idea of a convolutional neural network. Convolutional neural networks are known to be very good at processing sequences, and more specifically audio samples, because they have an ability to recognize patterns inside a sequence. Plus, they can be really scaled to arbitrary length, which is very important when dealing with the processing of audio signals. And lastly, they are highly parallel, which makes them efficiently trained and used once trained. Usually, when we use a convolutional layer when designing a neural network, we use it in combination with the idea of padding, which is a very common mechanism when processing a sequence with a convolutional layer. The idea of padding is to artificially increase an input sequence, either by adding zeros. So here we have, for example, an input sequence. We're going to add some zeros at the very beginning and end of the sequence to artificially increase its length. We can also use mirrored padding or reflection padding. There are many types of padding, but I'm going to stick with the zero padding. And the very goal of this mechanism is to basically allow to apply a convolutional kernel onto that sequence and produce an output that has a coherent output shape when regarding the input layer. So here we have an input sequence that has 4 samples, and when processing it with a kernel of size 3, we're getting an output sequence of size 4, which is pretty nice. The problem is using padding when addressing real-time processing of audio signals is going to cause some problems. Because when dealing with real-time audio streams, we don't have access to the full sequence yet, since it's basically not recorded. We would rather have access to buffers, which are fixed-site chunks of audio. And if we try and naively apply the convolutional operation on those buffers by first padding each buffer individually and then applying the convolution operation, what we're going to do in the end is basically introducing some discontinuities in between buffers here. And this discontinuity is going to mess with the convolutional layer ability to recognize patterns, and we're going to see that in the output of the convolutional layer, there's going to be some discontinuities too. For classification tasks, it can result in degraded classification performances. And for generative tasks, it can result in audio clicks, which is really not a good thing to have. Thus, previous work have tried to address this problem by introducing the idea of causal convolutions. This is the exact same thing as switching a filter from regular form to causal form. And the idea is really to, instead of given a sequence considering both left padding and right padding, use only left padding by reconfiguring the padding mechanism into its causal form. And the very cool thing about that mechanism, this causal convolution, is that it's only leveraging present and past samples, which is very important when you think about it when dealing with audio signals. The next buffer is not recording yet, so you can't really leverage it. So once you have this causal convolution, you can easily apply a convolution over it. You're going to get the same kind of output as in regular convolutions. And the second mechanism that's going to make you able to resume the operation when dealing with the next buffer is to basically cache the end of this sequence and use it to left pad the next buffer, so that when you apply the convolution operation onto that sequence, it acts as is. It's basically the full continuous sequence without any interruption nor discontinuity. So when using both causal convolution and cache padding, we make the model streamable, as in able to process audio streams when comparing to only processing pre-recorded full sequences. The problem is that most of the state-of-the-art in deep convolutional layers applied to audio processing is non-causal, meaning it really leverages future samples when processing a sequence. So if you want to basically apply the causal convolution thing to those models, you're going to have to convert this model to a causal state, which first might not work, because switching a model to causal is constraining its ways to process data, so it might be a more complex problem. And plus, you're going to have to retrain the model from scratch using the causal reconfiguration, which is sometimes expensive when considering large models such as Jukebox. And more generally, there is currently a lack of accessible tools for integrating general deep learning audio models inside real-time audio processing frameworks. Thus, in this work, we propose both a method to make any convolutional model streamable, both causal and non-causal convolutions. Our method is compatible with already trained model. You don't have to retrain it from scratch using some kind of causal reconfiguration. Our method yields a perfect reproduction of the original model behavior, and this comes at the expense of a minimal model latency when processing a stream. In addition to that, we propose a framework to easily build, export, and interact with deep audio models in real time using the PyTorch framework. So our main idea to allow the use of non-causal models on audio streams is the idea of post-training causal reconfiguration. So basically, you start by taking the original model, either causal or non-causal, and you're going to train it regularly using its original training strategy. Once the model is trained, you're going to basically reconfigure each convolutional layer to only use causal padding, and enabling the activation, the cache padding mechanism in order to allow the resuming of operation in between buffers. So that might work for very simple convolutional networks, such as just stacked convolutional layers. But once you start considering more complex layers, such as residual layers, for example, this causal reconfiguration is going to cause some problems. When we look at what a residual layer is actually doing on an input sequence, during training, it's basically taking the input sequence, it's copying it, then apply a convolutional operation onto that, and it's going to take the output of this convolution and add it with its input in order to produce the final output of the layer. So that kind of layer is widely used, and the problem is if we train the model using this very specific configuration, it's going to learn to associate very specific inputs with very specific outputs. Thus, when we take the streaming configuration, which is basically taking the original layer and switching the padding from non-causal to causal, we're going to make some kind of misalignment between the input and output of the layer. Thus, when looking at the output of the convolution, we can see that we can't really sum them together as during training, since there is a mismatch between input and output of the convolution. What can be done to address this problem is basically adding some delays inside the architecture of the model to realign the inputs with the output of the convolution, enabling us to basically regather input and output as in during training, and caching the leftover sample for later processing. And this method of introducing delays to realign the model once reconfigured into causal form can be applied for basically strided convolutions and more generally parallel computation branches, which encompass most of the existing architectures leveraging convolutional layers. So we test this method using the Rave model, which is an autoencoder that we've proposed almost a year ago now. For the context, it's an autoencoder that's applied directly on the raw waveform, so you have an input audio signal that goes through a convolutional encoder. This convolutional encoder produces a compact latent representation that has like many dimensions from 4 to 16. And this representation that is inherently more compact and supposedly high level is going to go through a convolutional decoder that is trained to try and reproduce the input sample. This model is operating on 44 kilohertz audio signals and can be used for timbre transfer or unconditional generation. Is reasonably fast for a deep learning model, around 20 to 80 times faster than real-time on CPU, and is even 4 times faster than real-time on a Raspberry Pi 4, which is pretty nice. A very simple way to take this model as it is and apply it on stream is to use like a very simple overlap add technique where you apply the unchanged original model on overlapping chunks of signals and then use crossfades to smooth out any discontinuities. We test three configuration, the 50%, 25%, and 0% overlap factors. And basically what we're looking at here is seeing if this method is yielding the exact same results as the original model when applied on a sequence. So we use a spectral distance between y full, which is the full output of the model applied on a sequence, and y buff, which is the buffer-based output of the model, whether it's using the overlap add method or our post-training causal configuration method. And what we can see is basically for all overlap add baselines, the reconstruction error is decreasing with increasing buffer size, which is to be expected. The worst overlap add method is obviously the 0% one, since you have all the discontinuities appearing during inference. The best one is, again, the 50% overlap method. But all of those methods still yield some differences between their output and the original model outputs, whereas our method is exact and reproduces the exact same behavior as the original model when applied to the fully recorded sequence. From a computational perspective, the memory usage for both model is for both methods is quite the same. Regarding the real-time factor, we can see that the worst one is the 50% overlap, which is again to be expected since it's working on 50% more samples. The best one is the 0% overlap, and our method lies in between the 0% and 20% overlap since it's adds some overhead when processing due to the need to cache some tensors at some point. We release a library called Cacheconf, which is freely available on GitHub following that link or QR code, and that enables the easy creation of streamable models, both causal and non-causal, automatically handling alignment problem and cache mechanism, which is compatible with the TorchScript programming language. Like embedding language. And basically, if you want to take a very simple model such as this one, which is simply a concatenation of two convolutional layers, you can switch that model to a streamable one simply by switching from torch NN as Cacheconf as CC and replacing the nn.conf to cc.conf. And by simply setting a flag to true or false, you're going to enable the reconfiguration and cache padding mechanism so that it's able to process streams. We also provide an external for max MSP and pure data. That's basically an interface for PyTorch that transforms PD and max MSP audio signals into tensors that PyTorch can process. It's compatible with both CPU and GPU computation. We are supporting ARM64 and Intel architectures. We're also supporting NVIDIA GPU computing, and we are about to support AMD and Apple GPUs in supposedly a few months. And Untilt is basically compatible with any streamable models, whether it is a convolutional model, a recurrent model, or even not a regressive transformers. The only requirement is that your model is fast enough to process things in real time, and that it is streamable with suited, cached, and resuming operations. It has a dynamic configuration buffer so that you can lighten the weight on your CPU, and you can dynamically configure your model during synthesis. To wrap up this presentation, I'm going to show you a quick demonstration of an Untilt used in real time. So let's say you have an input sample that sounds like this. You can apply a model trained on speech and reconstruct this input by simply instantiating an Untilt. You can also switch between models using one trained on Darboka, for example. And that's basically going to reconstruct the audio signal on the fly without much latency. And the cool thing about an Untilt is that it also allows you to basically go into the model, and for example, Rave is an autoencoder, you have an encoder and a decoder. So you can access both methods using an Untilt. For example, here, the first, third, and fourth dimension of the latent space remains untouched, while the second one is manually defined by a slider. And you can see how you can interact with the generation by simply moving the slider. So that's all for me. Thank you very much for your attention.
Thank you very much. That was great. The animations were excellent. They were very helpful. Do we have any questions from the audience? Yes, in the back.
Hey, thanks for your work. Really super cool. I have been focusing so much on causal convolutional neural networks and have never thought of doing post-training causal reconfiguration. My question would be now, or I actually have two questions. First, did I get this correctly that there is no performance drop whatsoever, so that you produce the exact same output as the non-causal model would do?
Yeah, exactly.
That's great. Given that now, would you propose for any given task, for that you need to develop a model from scratch, start with, that needs to be streamable and causal in the end, to start from a causal architecture, or rather start with training a non-causal network and then apply your post-training causal reconfiguration?
Mm-hmm. It really depends on your end application. If your idea of what you want your model to do is really real-time intensive, as you want to have the least latency between the input and output of the model, you're going to have to want to basically go to fully causal during training. Because there is something called the receptive field of the model, which defines how much the model looks into the future to make a prediction.
Or into the past, yeah.
Or into the past, yeah. And basically, we can't predict the future and still have the same performances. So we have to somehow add this amount of looking ahead as a latency to the model. And it's inherently handled by the reconfiguration, but you're going to have some latency. For Rave, for example, you have a 300 millisecond latency when using the non-causal version, whereas you have something like 20 milliseconds of latency when using the causal one. So it really depends on your application in the end.
I see, yeah. We've been controlling the latency and the receptive field with dilating the convolutions. But yeah, okay, I see. So that probably would give me more options to control the introduced latency, probably to start from scratch. But still, super cool and crazy results. So yeah, thank you.
Thank you.
Actually, I have a question.
Yeah.
Anyone else? Give up my spot? Nope. You didn't go into it this presentation. There's also C++, well, the VST, sorry, target. For Rave. Was that also done using Torch script?
Yeah, definitely.
Okay.
There is that thing called libtorch C++, which is a C++ version of PyTorch.
Yeah. That's how Tilde works as well, right?
Yeah.
And my follow-up question is, have you tried doing a custom implementation of Rave? I'm interested in how the performance compares with this sort of Torch-generated version versus a custom one using Eigen, for example. Have you looked into that?
What kind of custom implementation?
Just making your own C++ implementation of Rave, like coding your layers and importing your weights or exporting more.
Yeah, I think it would be like a major overhead in terms of development, but maybe a very good improvement in terms of performances.
Because I played with Rave. We had a quick chat before with an artist that you know and follows you, and it's very fast already. I was very impressed by the CPU use. It was below 5%, I think, on a not-so-new MacBook. So I'm wondering if maybe TorchScript is faster.
No, there is a trick with the 5% CPU usage. I'm using a different thread that's not taking into account during computation.
Right, okay.
It might be like maybe a 60 to 70% of usage. So.
All right, maybe
yeah,
we talk after
I'm
this.
sorry about that.
I'm happy I asked. Thank you.
You're welcome.
Any final questions? Okay, in that case, thank you very much,
Thank you.
Antoine.